Hey, what's up, guys? So 2064 minimize maximum product distributed at any store. This problem is the legal context, and I solved this near the time limits. So I didn't solve the number 4 problem. I'm not I'm not still not very good, but this is I still solve this. So given an integers including n special retail stores, there are product types of vary amount, which are zero indexes integer quantities, and the quantities I represent a number of products of I product type. And you distribute all product to retail store found. The store can only be given at most one product. So there is a store, right? And each store can at most put one product type, right? So this is the question. But you can take any amount of it, right? And you need to minimize the maximum number of products you are given any store. Okay, so for example, 6, 11, 6, your answer will be 3 because you can put 11 to the first 4 of them, and then put 6 to be 3 in the rest 2, right? So total you got 3. And then for this one, there are 5, 5, 5, 5, 5. Okay, and then for this one, you only get this. Okay, so at the beginning, I don't know how to solve this. My idea is to first using the pigeonhole principle, right? So if my initial guess is that you can use the pigeonhole principle such that you total have 17, right? And then you can divide the 3 and then take the selling. Now you get 3, right? And you just check that where 3 is the answer, right? This is very simple, right? Because you just check that 11 divided by 3, take the cell, plus 6 divided by 3, take a cell. So it will give you 4 plus 2, which is a 6. By the way, this is a ceiling. Okay. So if you see 6, which is less or equal to the number of n, then 3 should be the answer. Right. So my idea is that I use the pigeonhole principle and start from I guess the answer. And if 3 is not the answer, I go to 4. And I go to 5, and I keep trying. But this will keep that, but this will not a linear time. This cannot pass, right? Because it will count. Right, so this is my my time is the solution, which is not very good. So basically, let me just go through a little bit. Right, so basically, I just compute the ceiling, right? Because this you can prove that this ceiling should be a lower bound by the pigeonhole principle. And you start from n minus 1, right? And then you just check that. You just check that where you start from 0, and then you count how many of them box you need. If it's greater than n, then you just add 1, right? And then you return the final. So your results will be time exist, right? Because so large, right? But you can pass like 160 solutions. Okay, so but after I think that I find there is a way to solve this, basically using the binary search. It's better than my original idea. Okay, so the idea is very simple. You just do the binary search, right? So you can have, let's say your answer, what is the smallest answer? Smallest answer should be 1, right? Because let's say this n is 17, right? So you can put each one of them, right? So the smallest answer should be 1. And the largest answer, what's the largest answer? Largest answer is that you only have like 2 boxes. And one of them must be 11, right? So the largest answer must be the maximum of the quantities. Right, so you have your left and the right. So you have your left and the right indices. Now you just do the binary search, right? Let's say you do the binary search. And then you get m. And you can easily check that where m is a suitable answer. Right, you just do all the quantities. Let's say G is a quantity divided by M, and count the selling, and then see whether this guy is greater or equal greater than N. If it's greater than N, that means your box. If it is greater than N, that means you need more box, which cannot be the answer, right? So that means your M is too small. So you should put your I become here. Right, so your I should be n plus 1. Otherwise, that you just keep going and try to find the max, try to find a minimum. Okay. So idea is that you go through m and you define the answer. You define the count. You count how many boxes you need. So this is a tricky part. If G is modulo can modulo by M, then you should add G divided by M. If G is modulo not divided by M, then you should add 1. So for example, so in this case 3 is the answer, right? So 11 is not divisible by 3. So you are doing that 11 divided by 3 and plus 1. Okay. And then you check the whether your box. If the answer is greater than the number of boxes you can use, that means the number of boxes. That means this M is too small. So you need to I equals M plus 1. Otherwise, it's less than equal to N. Then you try to push your answer, right? So J equals to M minus 1. You will try to find a you try to find a maximum of it, right? Which you can get into. Right. But finally, so after all this step, you will get something, let's say I. Now I do some final sanity check that check this I is the answer. If I is the answer, then I return Y. I. Otherwise, I return I minus 1. I plus 1. Okay. So this is the final sanity check. So I don't know why I need this, but if I don't get this, I cannot pass the results. So this is a sanity check. So you can use a binary search. And I think if you use a binary search, then in this guy, you need to compute the number of quantities, right? So this is the complexity should be number of quantities times the binary search, right? So it should be log of maximum of the quantities. Okay, so this is a complexity. And this should solve the problem because this Q is at most 10 to the 5. So n log n can solve this. Yeah, this is my idea. I'm not sure. It's probably not so good, but oh, okay, very nice. Okay, so see you guys next videos.